Sometimes we would like to invert a function, but it's not a one-to-one function and might fail the horizontal line test, and in that case we do the best we can. So consider the sine wave here. As our angle goes around the unit circle, we plug that angle into sine. Of course, we get this oscillation between -1 and 1. This function is not at all one-to-one. It fails the horizontal line test. However, we would like to be able to invert the sine function at least on a restricted subset of its domain. We could pick kind of any part of this wave that we want to anywhere along the x-axis, but I think we would all agree that the best we should do would be centered around the origin. So from this bottom left low point to this top right high point on this sine wave that passes through the origin is what we would call the principal branch of the sine function. This is where we will choose to invert the sine function in order to define its inverse arcsine. Now let me zoom in just on this one particular branch. Notice the leftmost point is -π/2, the rightmost point is π/2 on the axis. That means that the type of angles that we're going to plug into sine in order to generate this principal branch range from -π/2 through 0 up to π/2. That corresponds to the right half of the unit circle, but you have to be careful here because sometimes students want to call the bottom point 3π/2, but we don't want to do 3π/2 up to 2π and then drop that down to 0 and then continue to π/2 because that doesn't give us a nice smooth piece of the sine curve. So in order to get this nice smooth branch that's connected, we have to think of this as passing from -π/2 on the left through 0 up to π/2 on the right. This is the part of the sine wave that we're going to invert, which means that we can reflect it over the line y = x to generate a picture of what the inverse must look like. So y = arcsine of x must take this particular form. The domain and range for our principal branch of sine are going to reverse themselves to give us the domain and range for arcsine of x. So the domain of arcsine is -1 to 1. Those were the outputs from the sine function. And the range goes from -π/2 at the bottom up through π/2 at the top. So while the sine function we think of as a function on all of r, so we could graph sine and we would get oscillations down the real axis, y = arcsine of x as we've defined it only exists as you see it in this picture. So it's just this little segment. It has a left endpoint and a right endpoint. Since we had to restrict y = sine of x in order to invert it, we need to carefully address how to compose sine and arcsine because they are inverse functions but only on a restricted subset of the original domain of sine. So it's not fair to always say that arcsine of sine, sine of arcsine wipe each other out. So first let's recall what sine as a function does. I might say sine of x, but what is x? Well, it's an angle. So if it helps, I could switch over to theta. So notice that sine of theta takes you from an angle to a ratio of sides. By SOHCAHTOA, we often call that ratio opposite over hypotenuse on some right triangle. So let me sketch a right triangle here. I'll call this angle theta, and then the opposite side is over here. The hypotenuse is the long side opposite the right angle, and sine of theta is opposite over hypotenuse. Opposite over hypotenuse is just some ratio, it's a number. Let me call that ratio the letter u. Arcsine is going to take us in the opposite direction. So arcsine of u will take us from that ratio back to the angle. Arcsine of u equals theta, but here we have to be careful. What we plugged into arcsine had to be between -1 and 1 because that's the domain of arcsine. It wouldn't make sense to plug in any other type of number. And then the theta that is returned to us will be a value between -π/2 and π/2 because that's how we defined our arcsine function. So let's address now how we would compose these inverse functions. Well, if I take sine of arcsine of x, it better be the case that x is between -1 and 1. It wouldn't make sense if it wasn't. In which case, sine of arcsine of x will always be x. To see this, Notice we're going to start with an x value between -1 and 1. We first plug that into the arcsine function. That will return us a theta value between -pi/2 and pi/2. Then we plug that theta back into sine, and then that's going to give us back a ratio between -1 and 1, which will exactly correspond to the x that we started with. So in this direction, sine of arcsine of x, so long as your x is in the domain between -1 and 1, these will just cancel each other out. The other direction for composition is a lot more complicated. So what is arcsine of sine of x? Well, the domain for sine of x is all real numbers. So it's often the case that you might be doing arcsine of sine of an angle which is not between -pi/2 and pi/2. So let's say x can be any real number. We plug it into the sine function, and what we get is a ratio between -1 and 1. So then we're doing arcsine of a number between -1 and 1. If we plug that ratio into the arcsine function, we're not necessarily going to get back the random number x that we started with. Instead, we're going to get back an angle between -pi/2 and pi/2, which is not necessarily the original x. It would be x if x was between -pi/2 and pi/2. Otherwise, it might be somewhere else on the unit circle, and it could be several revolutions away from the interval from -pi/2 and pi/2. And we have to look at the unit circle carefully to determine where between -pi/2 and pi/2 x would get mapped via this composition. It's easier to see with an example, so we'll do an example in a minute. So to summarize, as long as you're plugging in an x value between -1 and 1, sine of arcsine of x will give you back x. The other direction, though, is a lot more complicated. Arcsine of sine of x is going to return you back a value between -pi/2 and pi/2, whereas x could have been something like 200 pi. So let's do an example where we find arcsine of sine of pi/6. Here, of course, I've chosen a value which is not between -pi/2 and pi/2. 5 pi/6 is outside of that interval, so in order to evaluate this composition, we have to work back on the unit circle. Okay, so here's the unit circle on the left. Here's 5 pi/6 over here in the second quadrant. The sine of 5 pi/6 is a positive number. In fact, it's 1/2. So now we go over to the right side of the unit circle and figure out which angle between -pi/2 and pi/2 gives you a sine output of 1/2. And that particular angle is pi/6. Okay, so to work this out, we would say arcsine of sine of 5 pi/6 is arcsine of whatever that sine value is. So sine of 5 pi/6 is 1/2. Now, what is arcsine of 1/2? It's possible that that's just something you have to do in the calculator, but because this is a special angle, we can work it out by hand. It's pi/6 because pi/6 is the angle between -pi/2 and pi/2, whose sine is equivalent to the sine value at 5 pi/6. So that's how the composition works in this direction. It's not necessarily the case that arcsine of sine cancel each other out. Instead, arcsine of sine of x is going to send you to the angle between -pi/2 and pi/2, which gives you the same sine value as your original x. It's always going to land you in that interval. We go through a similar process in order to invert the function f of x equals cosine of x. Just like with sine, cosine oscillates. Its outputs range from -1 to 1. It does not pass the horizontal line test at all. So the first thing we want to do is identify what should be the principal branch of cosine. Notice it's not going to cross over the y-axis because the cosine function would not be 1 to 1. So we're not going to have the same principal branch as what we had for sine. So then we have to make a judgment call. where would we most like to invert this function? And what we've decided is that our left part of our principal branch should be the point 0, 1, and then we pick up this first downward swing until we reach -1. So this first pass downward to the right of the y-axis is what we identify as the principal branch of y equals cosine of x. By construction, y equals cosine of x is 1 to 1 on the principal branch over this restricted domain from 0 to pi. To see what the inverse function is going to look like, we can reflect it over the line y equals x. And now we have this short segment, which must be the shape of the graph of the inverse function arc cosine of x. Just like before, the domain and range of y equals cosine of x over the principal branch are going to flip to give us the domain and range for the inverse function. So the domain of the inverse function y equals arc cosine of x is going to go from -1 to 1, whereas the range, the set of outputs, is just restricted to the interval from 0 to pi. Notice that corresponds to the top half of the unit circle. This is usually easier for students. We don't have that jump going from -pi/2 to pi/2 that we observe with the sine function, where students have to call the values in the fourth quadrant negative angles. Here we just have the first kind of traditional revolution across the top half of the unit circle, which takes us from 0 to pi. And those are the names that we usually give those angles. So this in some ways is easier, I think, to grasp. Just like with sine, we've restricted the domain for cosine in order to invert it. So since we made this restriction, we have to take the composition of cosine and arc cosine carefully. Luckily, these functions behave similarly to the ones that we just worked with, sine and arcsine. So cosine of theta, we know, takes us from an angle to a ratio of sides. For cosine, that ratio is adjacent over hypotenuse. Once again, let's call this ratio u. Arc cosine of u is going to take us from that ratio, which must be a number between -1 and 1. No other ratio would make sense. And then it's going to give us back the angle between 0 and pi, whose cosine value is exactly the same ratio. So arc cosine takes us from the ratio back to an angle. What happens when we compose them? Well, just like a couple minutes ago with sine and arcsine, cosine of arc cosine of x always makes sense and returns you back x. Here, of course, x must be a number between -1 and 1, otherwise you couldn't even plug it into the arc cosine function. So those two functions invert in that direction without any restrictions. For the other direction, arc cosine of x is x if x were an angle between 0 and pi. Otherwise, just like before, x actually could have been anything. It could have been 200 pi over 7 or something like that. In which case, we must compare our angle to the principal branch of cosine. Namely, we have to figure out what angle between 0 and pi would give us the same cosine value as what x is giving us when we plug it into cosine. Once again, let's look at an example. So find arc cosine of 4 pi over 3, where here, what we're plugging into this composition is not an angle between 0 and pi. So this angle 4 pi over 3 does not live on the principal branch of cosine. Instead, it's down here in the third quadrant. So what we would do is come down, figure out that we're in the third quadrant. What cosine value is that? It's actually going to be -1/2. So then I want to come straight up to the principal branch of cosine and figure out what angle would give me a cosine output of -1/2. And the angle between 0 and pi which does that is 2 pi over 3. Hence we write arc cosine of 4 pi over 3 is arc cosine of -1/2. And then we say arc cosine of -1/2 must be an angle between 0 and pi, whose cosine value is -1/2. And again, that angle is 2 pi over 3. So arc cosine of 4 pi over 3 returns you back 2 pi over 3. Okay, the last famous function that we're going to invert is y equals tangent of x. Of course, tangent of x does not pass the horizontal line test, so we must determine what we should call the principal branch of the tangent function. I think it's quite clear here which one we would like to pick. It's this branch which comes down through the origin. On this particular branch of tangent, whose leftmost asymptote is x equals negative pi over 2, and whose rightmost asymptote is x equals pi over 2, tangent is a one-to-one function, so we can invert it. We can flip it over the line y equals x, and we get this curve which has two horizontal asymptotes. This is a graph of y equals arctangent of x. Notice its domain is actually all real numbers, but again, we have these horizontal asymptotes. So at the top, arctan is approaching pi over 2. And on the bottom, as we let x go to negative infinity, the graph of arctan of x approaches negative pi over 2. So this is arctan of x. And unlike arcsine and arccosine, notice its domain is the whole real number line. And that's because the range of tangent on its principal branch goes from negative infinity up to positive infinity. The range is the open interval from negative pi over 2 to pi over 2 because the domain of the principal branch of tangent is the open interval from negative pi over 2 to pi over 2. Notice in this case we're working on the same part of the unit circle as we worked on with sine and arcsine, namely the right half. So the types of angles which arctangent will return us go from negative pi over 2 up through 0 up to pi over 2. Once again, you don't want to say that that's 3 pi over 2 to 2 pi jump down to 0 pi over 2 because that doesn't give you one nice branch. Okay, now let's talk about how to use arctangent of x. Our approach to this will be a little bit different than when we discussed arcsine and arccosine. Just like with those functions, tangent takes us from an angle to a ratio of sides, opposite over adjacent if I drew the triangle, whereas arctangent takes us from the ratio back to an angle. But one of the real usefulness of arctangent, and it is a useful function, is to calculate angles, say the angle made by a ray pointing at some specified point, and the positive x-axis. So let's look at a couple examples. What angle does the ray which begins at the origin and ends at the point 34 make with the positive x-axis? So here's our point 34. Here's the ray in question, connecting the origin out to the point 34. And here's the angle theta that we're looking for. So I would like to calculate this angle using the arctan function. Okay, so let's drop an altitude straight down to the positive x-axis. We have a nice right triangle in the first quadrant. Because the y-coordinate is 4, the height of the altitude I just drew is 4. And because the x-coordinate is 3, this triangle is 3 units long along the x-axis. Since tangent of theta is 4/3, and the theta that we drew is between negative pi over 2 and pi over 2, right? So we expect to return a theta value actually between 0 and pi over 2. We can immediately invert and say that theta is arctan of 4/3. So here I don't need to find the hypotenuse or anything like that. Just using the x and y coordinates, I can basically say that theta is arctan of y over x. That's not a famous value on the unit circle or anything like that. So what is arctan of 4/3? In a calculator, that's about 0.93. That result is in radians. Or equivalently, that's about 53.13 degrees. Okay, let's look at the second example. What angle does the ray which begins at the origin and ends at the point negative 10 to, that's over in the second quadrant, make with the x-axis? So here's our point negative 10 to. Here's the ray in question. Here's the angle that we actually want to find because I want to measure off the positive x-axis, at least the way it was phrased in this problem. Okay, so just like before, I'm going to drop an altitude straight down to the x-axis over in the left half plane. And notice the right triangle which we've created actually has the supplement of the angle that we're looking at. Let's name that angle alpha. We can say that tangent of alpha is opposite over adjacent, so that's 2 over negative 10 the y-coordinate over the x-coordinate. Now, a word of caution here, we are over in the second quadrant, which is not part of the unit circle that we identified when we're relating tangent to arctangent. However, the domain of arctangent is all real numbers. So I don't have to be too concerned actually at this point. I can go ahead and take the arctan of both sides of the equation above. Therefore, we compute arctan of 2 over negative 10, which is approximately negative 11.31 degrees. Why is it negative? It's negative 11 degrees because that's referring to the principal angle between negative pi over 2 and pi over 2, which is the range of arctan. So we should think of this angle as if I extend our ray over to the fourth quadrant, it's negative 11 because we've measured down, so 0 is right in the middle. We measured down all the way down to negative pi over 2. We would measure up to pi over 2, etc. So since I measured down to get to this angle, it's negative 11.31 when we plug 2 over negative 10 into arctan. Therefore, theta would be 180 degrees minus 11.31 degrees. So we recognize alpha as 11.31 degrees. This gives us a theta value of 168.69 degrees approximately. So this is the usefulness of arctan. If you're given an xy coordinate, you can compute the angle formed. If your angle is in the right half plane, then immediately it's arctan of y over x. In the left half plane, you have to do a little bit more work as this example demonstrates. But the key idea is arctan of y over x returns you a way to find the angle formed by a point in the xy plane and the x-axis.